Okay, chapter 5. Now, chapter 5 is in your ck12.org textbook, so make sure that you have the PDF copy downloaded or you are able to access um, the PDF versions online. Okay, so before we get too far into this, I want you to brainstorm right now. What do you know about evolution? And I want you to pause this video and make a list of what you do know about evolutionary biology, and I want you to put that on the board. Okay, chapter 5 is going to be about evolutionary biology, and we're going to start with the history of life and really the development of our planet and how everything kind of started here. Okay, so section 1, we are going to be looking at the fossil record. Okay, so fossils are really preserved remains or traces of organisms from the past. Most of the time our soft portions of the organisms have decomposed and they decay very quickly. However, we do sometimes see hard portions or remnants of animals left behind. Now, the bones that we see from dinosaurs are not actually bones. What has happened is that we have seen sediments fill those spaces in between the bones, because bone is very porous, so lots of little holes in it, and that is minerals that is actually calcified, and that's what's left. And so you don't actually have DNA or bones left over from this. Most of the time we don't see fossils unless you have an abundance of animals die at one time, which is a mass extinction, or you have to have the right circumstances. Now in South Dakota we're very lucky. We have things like the Mammoth Site, which is an active dig for fossils. If you ever get a chance, go to the School of Mines, go to their geology department. They have an amazing collection of fossils, and full dinosaurs and some index fossils as well. Okay, but they are preserved remains. And so if we think about some of this stuff, we've been looking at the fossil record for about 3.5 billion years. And so when we say it's unfolded over 4 billion years, it's getting close to that 4 billion, but it's not quite there. Our first fossils were found for prokaryotic organisms, and then we found our eukaryotic, which are much, much more plentiful and easier to find. Not every organism has a fossil, and so we know that we have some gaps in our fossil record because we just simply don't have those organisms available to know anymore. But when we do find fossils, we can use two types of dating. One is relative dating and one is absolute dating. And so relative dating is kind of a guess. It's relative based on where it's found out in the rock layer. So if you think about your pile of dirty laundry that's in your room, at the bottom of the pile is probably going to be the oldest clothes, or the clothes that you wore like a long time ago. And at the top of the pile is probably the clothes you wore yesterday. And so relative dating is looking at those layers, and it's kind of comparing, it's assuming how old something is by what's kind of around it. And so it's not an exact science, and it's not precise. However, we do have an absolute dating, and absolute dating is has a lot more precision in it. And basically with absolute dating, we're able to use carbon-14 dating. Now, carbon-14 is a radioactive isotope that we find within all living organisms, including yourselves. And so once we die, carbon-14 breaks down very, very slowly. And so because it breaks down so slowly, we can actually determine how old something is by the amount of carbon-14 that they have in them, and what is left. And so that one's a little bit more precise, and so it's not 100%, but we have a pretty good approximation of how old things are. And so in your textbook you do have an example of relative dating and absolute dating in figure 1.3. And so we're seeing the older material is at the bottom, the younger is at the top, and so we can kind of look through there. Now we have what we call a molecular clock. Now this is somewhat new, it's not something we've been using for a long time, but a molecular clock uses DNA sequencing, and it estimates the basically how old a species is, or how many related species that we have to that. And we can actually use a molecular clock to estimate the geologic history of a species and common ancestors of that species. And so one thing that's really kind of cool is that we can take DNA from us, and you can actually trace it back and find out your origins of where you're from. A cool website is like Ancestry.com. It takes about $100. You can do a DNA test, and it tells you where your origins are actually from. Are you going to be Scottish or Irish or Asian, or wherever you're from on the planet? It kind of dates that back based on your DNA. And so that's what the molecular clock is using. It's using your DNA to estimate where you fit into the geologic time sequence and scale. Some species have a greater accumulation of DNA, and so they haven't really changed a whole lot, or their common ancestor is still present. Like alligators, it's a little bit easier to kind of date them because they're still around. They were around millions of years ago, where humans were kind of a new species, and so our molecular clock doesn't show as much. Also with this DNA, we're looking at migration patterns and how far we've moved and the rate at which the DNA has spread through an entire region. And so it's, again, not precise data, but it's something we can kind of look at. Also, we can look at similarities between the DNA. And so when we start comparing these similarities, so we look at a chimpanzee compared to a human. So a chimpanzee has a 98% compatibility rate, or DNA comparison, to a human being, which tells us we probably have a common ancestor. A mouse is about 85%, chickens are 60%, and fruit flies are about 44%. Well, we can see that we're one, part of the kingdom Animalia, so we should have something in common with all of those species. Two, as we start getting closer to vertebrates, which we are, you can see that chicken, a mouse, and a chimpanzee are closer in relation than a fruit fly, which is invertebrate. And then when we start looking at mammals, the mouse and the chimpanzee, again, have more DNA in common than a chicken. And when we start looking at primates, which we're part of, we can really start to see that, hey, yeah, we do really have a common ancestor here. And so these are just tools that we can use to try to figure out how species are related and common ancestors in them. Then we have the geologic timescale. The geologic timescale, if you remember back to 8th grade, is just basically a tool that shows the start of Earth's history to now. And so it's just kind of a timeline that we can use to do this. And you do have figure 4.1 in your book does have a geologic time scale, and you can kind of see the different super eons, which we have one, which is Precambrian. We have our eons, and then we go into our eras and our periods. And so these are all broken down into smaller portions. Just remember that we are part of the Cenozoic era, and we're part of the Quaternary period. And so humans are actually, we're fairly new to this whole division of time. Basically how we break this down is they're based on geologic changes, climate, and evolution of life. And so you're going to see when we start talking about our different geologic timescales, we have a major mass extinction right before the next one starts. Also, we'll see like an ice age starting to occur. And so when we look at what's going on right now with climate change, we can really start to see that we are going to have a mass extinction occurring, which we can see that now we have a ton of endangered species. We have hundreds of species going extinct every day. And then also we're going to see another ice age. Well, if we look at this, we're seeing every time before an ice age you have a warming of the climate, which we are doing right now, and then you go into a massive freeze. And those are based on different things that we've seen throughout history, like an asteroid's hit, volcanic eruptions. Those have all played out. We'll talk about each one of these eons, eras, and periods a little bit more later on. But it's really important to understand that these are all tools that we can use to kind of put together, hey, what has happened on the planet and where are we sitting at?